Under the Mathematics of Artificial Intelligence playlist, we continue with the loss function that teaches AI. We came across the idea of loss function in the introductory video, and here we are looking into the idea of loss function in some more depth. The loss function that teaches AI. So here we are going to encounter ideas like cross entropy, optimization intuition, and neural network training. And the objectives are as follows. After by the end of this lesson, you should be able to explain what a loss function is and why machine learning models need one. Then understand why cross entropy is the standard loss function for classification, and compute cross entropy manually, develop an intuitive understanding of optimization, explain how neural networks learn from errors, and implement cross entropy in Python. So, of course, you also want to be able to train a simple neural network using cross entropy. Let's move on, shall we? Now, the first part talks about why AI needs a teacher. So, why does artificial intelligence need a teacher? Why does it need to be corrected from time to time? Why does it need to be taught? So imagine the student taking a mathematics examination. After completing the exam, the student receives a score. Now, if the score is low, the student studies harder and corrects their mistakes. If the score is high, the student knows they are improving. And but then machine learning models learn in exactly the same way. So every prediction made by an AI model is compared with the correct answer. So, there's a training and there's a prediction based on the training compared with the reality. Then the difference between the prediction and the correct answer is measured by a loss function. That's like the gap between the correct answer and the wrong and the answer by the model. So the loss function then acts like a teacher by answering one question: how wrong was the prediction? Okay, so the smaller the loss, the better the prediction. So if the loss is like zero, so it means that the model is getting a perfect answer. So the larger the loss, on the other hand, the worse the prediction. So that's why AI has to be taught. Uh, AI models have to be taught. Now, let's talk about the learning cycle. So every machine learning algorithm repeatedly performs four basic steps. So you input your data, that can be in form of prompt or some data set or whatever. And then there's a model prediction. That is like the answer your AI gives, depending on the records it holds. And then a loss is computed to compare what the model is predicting and reality. And then the parameters are updated and the process is repeated until a good enough answer is obtained. So this repeated cycle gradually improves the model, and each repetition is called a training iteration. So each step is a training iteration. So, and we expect to see that as many times as possible until we get the desired results, depending on the context one is operating in. Now, let's talk about what a loss function is. So, a loss function measures the difference between the model's prediction and the correct answer. Mathematically, loss is actually a function of both prediction and the true label, the true result. So a good prediction produces a small difference, a small loss between prediction and true label, while a poor prediction produces a large loss between prediction and true label. So the objective of each machine learning is therefore very simple: minimize the loss. So every machine learning algorithm is just basically minimizing the loss, the difference between prediction and the true situation. Now, let's look at an example here. Suppose we are building an image classifier. So we want to be able to classify images we feed to a model. So suppose we are to build an image classifier. Let's say the true image is a dog. So the neural network then predicts that it is a dog by with a probability of 0.92, and it is a cat with a probability of 0.05, and a bird with probability 0.03. Now this prediction is excellent for sure, but then the loss should therefore be very small because the prediction is 92%, which is as close as possible to 100, right? So now consider another prediction. If dog is now 0.15, cat is 0.80, bird is 0.05. The model is very confident that the image is a cat. But unfortunately, the correct answer is dog. So the prediction is poor. So the loss should therefore be very large. So in the first case, we have a small loss. And in the other case, we have a very large loss. Now, question is about the next question to answer will be about the different types of loss functions. Now, different machine learning problems require different loss functions. For instance, if you have a regression algorithm, so the typical loss function will be the mean squared error. for a binary classification, so you want to tell whether something is there or not, or whether something is black or white, or whether something is tall or short, binary classification, you have a binary cross entropy as the typical loss function there. And for multi-class classification, you have categorical cross entropy. For language models, you have cross entropy. For object detection, you have combination of multiple losses. So for almost every modern classification model, including image classifiers, speech recognizers, and large language models, the most commonly used loss function is cross entropy. So talking about image classification, speech recognition, and large language models, we talk about cross entropy. Now let's go and see, why not just count mistakes? Suppose two classifiers both predict the correct answer. For instance, model A says dog, so what you have is a dog with with probability 0.51 and cat 0.49. And it makes the correct prediction because the dog is actually the correct image. So the probabilities are pretty close, but it still manages to get the correct prediction. On the other hand, we have a model B which predicts that the image is a dog with probability 0.999. That's 99.9% accuracy. And then cat is 0.001. That's just 1% that it is cat, which is also correct, right? Now, if we simply counted correct and incorrect predictions, both models would receive exactly the same score. However, model B is clearly much more confident. So model A is correct, model B is correct, but model B is more confident in its prediction compared to model A. So model B is clearly much more confident. So a good loss function should reward confident, correct predictions and penalize uncertain predictions. So cross entropy does exactly this. So it's more like you're looking at students who wrote an exam, and if you just want to look at those who pass, so once you have let's say 50% is the pass mark. So somebody who scores 50% has passed, right? But then there's somebody there who got 100% also, who has also passed. So, but here, the idea of loss function rewards the closeness of the pass mark to the maximum marks obtainable. So imagine the person with 100% is just is on point. Like the loss is just zero. There's no difference between the accurate score between the maximum score and the mark obtained. But the person with 50%, of course, the person has passed, right? But you have like let's say 50, technically between 50 and 100. So they are both passed, but it's important to penalize uncertain predictions to reward people who passed well compared to people who just passed. So cross entropy does exactly this. Now we talk about probability refresher now. Now imagine cross entropy operating on probabilities. For example, you have dog with probability 0.7, cat 0.2, bird 0.1. The probability satisfies the fact that 0.7 plus 0.2 plus 0.1 is 1, because every probability should lie from 0 to 1. No probability less than 0, no probability greater than 1. And in the probability distribution, all the probabilities must add up to 1. So that's basically the idea here. So these probabilities are usually produced using the softmax function, which we actually saw in a previous video, and we're going to touch on again here. Now, understanding cross entropy. Cross entropy measures how surprised the model should be by the correct answer. So if the model assigns a high probability to the correct class, the surprise is small. And then the loss is also small. So if the model assigns a low probability to the correct class, the surprise is large and the loss is also large. Therefore, higher probability for the correct answer implies smaller loss, and smaller loss means better model. So we want our models to have as small a loss as possible. Then we go on to talk about the general formula for loss now. So here, for a classification problem with multiple classes, we have the loss function defined by this. I think we've come across this formula before. It's closely related with the idea of information theory as proposed by Shannon. So in fact, I think it's called Shannon function or something like that. So L is equal to minus summation from I equals 1 to n of yi log pi. So where yi is the true label, that's for one hertz on when it is 1 hertz encoded, and pi is the predicted probability for that label, and n is the number of classes. So in that case, we're able to get the entropy, the loss. So talking about 1 hertz encoding, now imagine suppose we have three animal classes. We have dog, cat, and bird. So if the true class is dog, then the 1 hertz vector will be 100, that one for dog, others 0. Then if the true class is cat, we have 010. So one for cat, that is in between dog and bird. So dog 0, bird 0, cat is in between 1. Then if the true class is bird, that's 0, 0, 1. So only one element equals 1. In each case, that's one head, the idea of one head on encoding, just to signify that particular thing we're focusing on in that case. So all other elements are 0. Well, as far as one, that's why it is called one hot encoding. So you only assign 1 to the to the expected result, to the answer you're focusing on, and others are 0. So we then have a simplified formula because only one value of yi equals 1 in each case. The summation simplifies dramatically to the cross entropy loss becoming L equals minus log p, in the sense that um okay, maybe yi is only 1. So if you do that, just have log pi. So because in the case of one hot encoding, that's what you get. So where p is the predicted probability assigned to the correct class. So this simple equation is one of the most important formulas in deep learning. So this simple L equals minus log p, because of one hot encoding. It's one of the most important formulas in deep learning. And then we go ahead to talk about why cross entropy uses a logarithm. So the logarithm has several useful properties. We see the logarithm on the Shannon formula, so to speak. We see the log here, and then when we even simplify it in the case of one hot encoding, we still have a log here. So the question is, why does cross entropy use a logarithm? So the logarithm has several useful properties. First of all, it rewards confident correct predictions. Then two, it heavily penalizes confident incorrect predictions. Then it produces smooth gradients for optimization. So the graph of minus log p drops rapidly as p approaches 1. Because log at 1 is 0 in the first place. So this makes cross entropy an excellent objective for learning. So let's look at these cross entropy values. Okay. Okay, let me just make it big first and then shrink it later. So cross entropy values for correct probability, you have 1.00. So if you have a correct probability of 1.00, then the loss, which is minus log p, will be minus log 1, which is 0.00. So this is a perfect prediction. If it is 0.90, the loss is getting bigger. That's 0.105. If the probability is 0.8, the loss is 0.223. 0.5, 0.693, 0.21, 0.609, 0.1, 2.303, 0.01, that's 4.605. These are cross entropy values. Now, notice that the loss increases very quickly as the probability assigned to the correct answer decreases. So, with lower probability, you have bigger loss, basically. And that happens fast because we are using the log. So, imagine example one. The correct class is dog, for instance, and the model predicts dog to be 0.9, cat to be 0.08, bird is 0.02. Now, the correct probability P is 0.90. Therefore, L is minus log 0.90. So, using the natural logarithm now, L is equal to, so this log is not log to base 10, it's log to base E. That's natural logarithm. So, L is 0.105. So, this is a very small loss because the model was highly confident and correct. So, for example, 2 now, imagine the prediction now has class and probability dog 0.4, cat 0.35, bird 0.5. Now, the correct probability is p equals 0.4, which correctly predicts dog, by the way, but the probability is pretty small. Therefore, we have L is minus log 0.4 and L is 0.916. So, you can see it's the last time we had 0.10. Here we have 0.916. So the loss is much larger because the model was much less confident. So you can see how fast that grows. And in example 3, suppose the model predicts that dog is 0.01, cat is 0.9, bird is 0.01. The correct class is dog. Therefore, you have that L is minus log 0.01, which is 4.605. That's big. So this extremely large loss tells the optimizer that the model made a serious mistake. So when you say a loss that is just suddenly large, so that tells you there's a serious mistake and you may need to check what's happening. So all those three examples, now we summarize them here. So import part, so you have the probability 0.9, 0.4, 0.01. So for each of the probabilities, now which line 5 says for p in probabilities in this list, then the loss is minus log p. Of course, you can only get from the maths library. That's why we have minus math.log p. Then you then print the probability to two decimal places, and then you print the loss also. So probability 0.9, the loss 0.105, like we got before. Probability 0.4, the loss is 0.916. Probability 0.01, the loss is 4.605, like that. Notice how the loss increases rapidly as the probability assigned to the correct answer decreases. So as the probability assigned decreases, you have the loss growing so fast. And here now we can visualize the cross entropy loss function. And see, because this one approaches zero fast enough as probability is increasing, that's why it's very good to use log. So you can look at this code. So here we have numpy matplotlib, then we have the probability. So we are looking at the probability from 0.001 to 1. Not now, why not 0 to 1? If we do log 0, that's undefined. So we have to start from something pretty small like 0.001, and then we stop at 1 for what probability is expected to be in 500 divisions. So the loss is now minus np dot log p, and then you plot all of this. So we plot p against loss and all that. So that's how we have this now. So as probability is moving towards 1, you see that the loss is dropping sharply. And as the probability is reducing, the loss is increasing so fast. I mean, the cross entropy loss is becoming so big. So here, the graph illustrates one of the key reasons why cross entropy is so effective. It's so effective. As the probability assigned to the correct class approaches 1, you see that the loss goes to 0. So as probability is coming towards 1, so the loss is dropping down so fast. Then when the probability assigned, I mean, the loss is dropping so fast. When the probability assigned to the correct class becomes very small. So as we move closer and closer to 0 here, so you see the loss is growing so big, it goes so fast. So this strong penalty encourages neural networks to assign increasingly higher probabilities to the correct answers during training. Okay, so that takes us to the idea of optimization intuition. Knowing how wrong a prediction is does not automatically improve the model. So the model must also determine how to reduce the error. So the process of reducing error is called optimization. So that's more like the normal calculus optimization thing we know. So optimization is the process of adjusting the model's parameters so that the loss becomes smaller over time. Mathematically, the objective is to minimize the loss, which is a function of theta over theta, where theta represents all model parameters, things like weights and biases, and L of theta is the loss function, which is a function of these parameters. So the goal of learning is to find parameter values that minimize the loss. So we have an intuitive analogy then. Imagine standing on a mountain in dense fog. You cannot see the valley below. However, you can feel the slope beneath your feet. Yeah, beneath your feet. So your strategy is simple. Slopes, feel which direction slopes downward, then take a small step downward. And you keep repeating that. Okay, you keep repeating that. Eventually you reach the lowest point. So machine learning optimization works in exactly the same way. So you keep descending the mountain until you get to the lowest point where the loss is minimized. So the loss function defines the landscape, that has been defined. Then the optimizer determines which direction to move. And then the gradient tells the optimizer which direction is uphill. So the optimizer simply works in the opposite direction. So if you, for instance, a good way to know if you're cycling or you're walking, if you have to exert more energy, it means you're going uphill. So if you discover that you're exerting too much effort, then you're probably in the wrong direction. So you want to go in the opposite direction where you can easily go downhill easily. I mean, you can easily go downhill. So the optimizer simply works in the opposite direction of what the gradient of uphill, basically. Now, talking about the loss landscape now, imagine plotting the loss as a function of the model parameter. So you have loss on the y-axis and weight on the x-axis. So as weight increases, loss also increases. As weight reduces, the loss also reduces. So the bottom of the curve represents the minimal loss. So the training attempts to move the model toward the minimum. So maybe if it started from somewhere here. So the goal is to come to the lowest point possible. That's the minimization loss of the loss function. So now, why optimization matters, right? Suppose the neural network initially predicts that, if the true image is dog and the true label, predicts dog and the true label is dog, probability 0.35. The image is cat and the true label is cat. So probability 0.4 for bed, 0.51. Now, the predictions are not very confident because, I mean, they are pretty close. The predictions are not very confident. So the cross and you have confident predictions when you have very high probabilities assigned to at least one or two, especially one. So the cross entropy loss is relatively large in that case. So after many optimization steps, the predictions can then become, so you have to keep doing, I mean, along the line, sometimes in machine learning, you do hyperparameter tuning to adjust parameters so you can get higher results. So in that case, you now have 0.99, 0.99, 0.97 like this. So here now you can see all the predictions are very confident, they are very bold. So the loss becomes much smaller in that case because we have bigger confidence, higher confidence. So optimization is therefore the mechanism that transforms poor predictions into good predictions. So when you do hyperparameter tuning in machine learning, what you're doing is optimizing. You're trying to fine-tune the parameters to see if you can get better results. So let's talk about gradient descent, which is one of the very important optimization algorithms. So the most, by the way, I mean, if you need to learn more about optimization, I have a whole playlist on numerical optimization techniques that talks about gradient descent, conjugate gradient method, and all of these things. Even things like genetic algorithm, differential evolution, and all that. So you want to check the playlist, just go to my channel and click on playlist and go to where you find numerical optimization techniques. So the most common optimization algorithm is gradient descent. So gradient descent repeatedly updates the model's parameters in order to reduce the loss. So the update rule is this: the new value of the weight, is equal to the old value of the weight minus eta, which multiplied by change in the loss function with respect to the model weight. So W is model weight, eta is the learning rate, and DLDW is the gradient. So the negative sign indicates that we move in the direction of decreasing loss. So it's more like going downhill because we are talking about a minimization thing. We are minimizing the loss function. Now, understanding the gradient, then, the gradient tells us, so, what's gradient here? The LDW. What does that really tell us? The gradient tells us if I change this weight slightly, how much will the loss change? Okay, that's what the gradient says. So a positive gradient means increasing the weight increases the loss. Then a negative gradient means increasing the weight decreases the loss. So the optimizer therefore moves in the opposite direction of the gradient. So because increasing the weight actually decreases the loss. So why move opposite the gradient? You see gradient descent. So it means you're moving down, you're moving away from you're moving in the opposite direction. So suppose the LDW is 5. This means increasing the weight makes the loss larger. Therefore, we should decrease the weight. So suppose instead the LDW is equal to minus 5. Now, increasing the weight reduces the loss. So if we increase the weight rather, we reduce the loss. Therefore, the optimizer increases the weight. The update equation automatically performs both cases correctly then. So, and then we talk about the learning rate. So we are trying to explain. So now we've talked about the LDW, and now we want to talk about the learning rate eta. So learning rate now. The learning rate controls the size of each optimization step. So the learning rate determines how fast you quickly get to the optimal solution, the minimum value of the loss function. So the learning rate controls the size of each optimization step. It is represented rather by eta, and the different learning rates produce very different learning behavior. So the learning rate tells you how fast you get to the solution. So and the learning rate also determines if you have to do more iteration or less iterations to get to the minimum value of the loss function. Now, talking about the small learning rate now, if you start from this uh, top value and you get to this minimum in the 1, 2, 3, 4, 5 steps. So the advantages of the learning of small learning rate is that that's a stable learning. So the learning is not dramatic. So you can easily trace what's happening. So you have some stability. Then you have accurate updates because the steps are very small. And then the disadvantage is that it's very slow training. So you need more compute power, you need more compute time to be able to work with very small learning rates. On the other hand, if you have a large learning rate, so you see small learning rates just going step by step. But for large learning rate, things happen so fast. So you can have a value coming down this time, next time it goes up, next time it comes down, next time it goes up, and so on. So that's for large learning rate. So the optimizer repeatedly overshoots the minimum. So training becomes unstable. So instability is attached to large learning rates as opposed to stability with low learning rates. So the loss may even increase in some situations with large learning rates. So, but then apart from the small or large learning rates, there's actually a good learning rate. So a suitable learning rate balances speed and stability. So it is fast enough but at the same time it is still stable. So typical values may include things like zero point 0.1 for eta, 0.01 or 0.001. The best value depends on the problem and the optimizer being used. So the problem you're solving and the optimizer being used will determine if 0.1 or 0.01 or 0.001 should be the good learning rates in that situation. Then we move on to minimizing a simple function. So to minimize this simple function, I mean, it's stuff of calculus, right? Suppose we wish to minimize the loss function L of, which is the function of weight, equals weight minus 3 raised to power 2. This function has its minimum at w equals 3. So if you plot this now, this is a parabola, starting from w equals 3 or so. Yeah, so the minimum value. Okay, I think let me demonstrate that so you can understand what I'm talking about. So we go Desmos. It's been a long time since I used Desmos. So there's the Desmos and see what that looks like. So w minus 3 all squared. So the minimum point is at w equals 3. So here, I have to use x. So I have x minus 3 raised to power 2. X minus 3 raised to power 2. Is that what we have? Yeah, x minus 3 raised to power 2. So we have the minimum value at this point. X is 3, y is 0, like that. So the function has its minimum at w equals 3. So the derivative now, the LDW, of course, we have to use function of a function, or we can expand and differentiate. But function of a function tells us bring down power 2, differentiate inside that is 1. That's 2 times 1, multiplied by the original expression and with the power reduced by 1. So you have 2 into w minus 3. Then if we can then begin with w equals 10, if our initial guess for the weight is 10, and we choose the learning rate to be 0 0.1, then we can then do the iteration and keep moving step by step this way. So in this case now, and that's where coding becomes important. Although we can do this manually because it is simple enough, but when the function gets very tricky, we may need coding is useful. So if we have the original value of the weight to be 10 and the learning rate is 0 0.01, so and we print the iteration. So, and then this is spacing here. Then the iteration, the weight, and the loss. So for I in range 10, so for different values of I, so we have loss is W minus 3 raised to power 2, and then we print I for, 10D, then here we print all of this. So, and in 10, that means from 0 to 9 there. So, and then the gradient is 2 times W minus 3. And we know ultimately that W is W minus learning rates times gradient. So if we run all of that, we end up having this situation. So initially, at iteration 0, we had 10, and then the loss was 49.00. I mean, we can still see the loss. That's at 10, right? 10 minus 3 is 7. 7 raised by 2 is 49. So we have that loss there. And then at 1 now, the weight changes. Now, instead of being 10, so we have 10 here initially, the learning with 0 0.1, 49 initially. So by the time we come to this next level, the weight is now 8.6, and then the loss is 31.36. So you can see as the weight is getting smaller, the loss is getting smaller with it. So by the time we get to the 10th step, we have the weight to be 3.93 and the loss is now 0.8827. Now, notice what happens during optimization. The weight moves closer to 3 because the minimum value is 3. So the weight is moving closer and closer to 3. In fact, let me do for you to really understand that, because 3 is the minimum value, the loss function cannot go lower than 3. So imagine if I make this one say maybe 100 will be too much. Let me just do 20. So you discover that it moves it drops sharply, and then when it gets to 3, it's stabilizing around that 3. In fact, if I do even let me even do 200, that's a lot, but let me just do 200. So you see, so at the end of, in fact, 200 is too much. Around, it gets perfect way before that. So it gets to be exactly like 3.00 at the 55th iteration. We started from 0. So around the 55th iteration, we already have this. But the loss function has also been like very close to 0 all the while. So, the minimum function is the smallest value of the loss function we can get there. So it will look like 50 iterations will be fine enough. So there's always a stopping criteria, like how far should you go based on the level of accuracy you want. Now, the weight moves closer and closer to 3. So the loss decreases every iteration, as we know. So eventually the updates become very small. So this behavior is exactly how neural networks learn. The only difference is that a neural network contains millions or even billions of parameters instead of one. So here we are using one parameter for all the parameters, which is not the reality. But this is good for demonstration purposes. So, but if you have many parameters, so that's why it becomes more complicated. So from the beginning, we already learned that AI is doing simple things on very large data sets, basically. You are doing very simple things like matrix multiplication. You are just adding things up. You are doing, for, chain rule on very many parameters. That's why it becomes complicated. So, for all of the things we've done now, so we've been want to get the optimization objectives. Now, this is us visualizing everything we've done over there. So the optimization objective is now here. So the minimum value is around here, which is exactly that 3. And then you have other points. So this is the starting point. So you keep coming until you get to this value down here. That's the minimum value we can get. So the graph shows a simple convex loss function, and a convex function has only one global minimum. So optimization is relatively straightforward because every downhill step moves towards the same solution. So it's easier to optimize when we have a convex function, for instance. And that is why there's a whole field called convex optimization. So real neural networks have more complicated landscapes. So neural networks contain millions of weights. So instead of a simple parabola, the loss surface becomes a very high dimensional landscape containing, you can have valleys and ridges and plateaus and saddle points. So instead of just having that simple parabola, right? Instead of just having that simple parabola that we had there, something like this, you can end up having uh, things as complicated as this. So imagine the loss function being like, it just has so many things attached and it just keeps going. So in this case, the work to get to the minimum value of the loss function is quite a lot more. So compared to that of a simple parabola. So although the geometry becomes much more complicated, the basic optimization strategy remains exactly the same. You compute the loss, you compute the gradients, you update the weights, and you repeat until you get what you want. So we have optimization during training now as follows. Every training iteration follows the same sequence. You have input data, you have a forward pass, you have your predictions, you have the cross entropy loss to compare the predictions and the true labels, and then you have the gradient computation again, and you update the weight, and you have the next iteration, and you keep going until you get you get results up to a satisfactory level. Now, what happens after thousands of iterations, right? Initially, predictions are mostly random, and then the loss is large. So after hundreds of iterations, predictions improve and loss decreases. After thousands of iterations, predictions become increasingly accurate, loss approaches the minimum, and the learning process is therefore simply repeated optimization. So you see, just like what I showed up here, you discover that from the beginning we started from 10 and it just kept going. So the weight, we know the minimum weight would have to be 3. So it's decreasing sharply, and then as around when it gets to 3 point something, it begins to slow down because I mean it slows down towards ultimately getting to, in fact, as at 49 iterations, we don't have, in fact, this 50th iteration, we still don't have 3, but you can already see that it's getting closer and closer to 3.00, which is the optimal result as shown on the plot right here. Okay, so optimization during training, that's what I just explained. Input data, forward pass, predictions, cross entropy loss, gradient of computation, weight update, and next iteration. Now, what happens after thousands of iterations? Okay, I've explained that also. The learning process is simply repeated optimization. That's basically what's happening. So after thousands of iterations, predictions become increasingly accurate and loss approaches a minimum, which is probably, in fact, minimum loss will be 0 at the end of the day as you approach the minimum weight. So here, you have the typical training curve, training loss curve. This is what it looks like. So, you have it sloping downwards this way. So as the training iteration goes, the loss becomes smaller and smaller, approaching 0. So here, the training curve typically decreases rapidly at the beginning because the model quickly corrects large mistakes. As training continues, the improvement becomes smaller because the model is already making good predictions. Eventually, the loss stabilizes near a minimum, indicating that further updates produce only marginal improvement. So, as you get closer and closer to the minimum, like in the case of 3 the other time, so you see that the updates only produce very tiny results as it approaches the minimum value you're looking for. So the key takeaways from what we have learned about the loss function is that optimization is the engine that allows machine learning models to learn from data. Remember these essential ideas. First of all, the loss function measures prediction error. The optimizer attempts to reduce the loss. The gradient indicates the direction of increasing loss. Gradient descent moves in the opposite direction, and then the learning rate determines the size of each update. Repeating this process thousands of times gradually improves the model. In the next section, we will combine everything we have learned to understand how an entire neural network is trained using forward propagation, backward propagation, cross entropy, and gradient descent. Okay, so watch out for where we get to talk about these other ideas like forward propagation, backward propagation, and all that. Now let's talk about some practice problems. So solve the okay, yeah, as usual, I get to solve two of this. So um solve the following problems without using a calculator unless instructed. Show all intermediate steps. Now I'll be solving 15 and 20. I'll solve 15 and 20. Yes. So here you can see questions one and two clearly. Then here you can see three to, okay, we can't show up to five for now. So you see three and two also clearly. Then you have five and six clearly. Seven and eight clearly. Nine, 10 and 11. Okay, 9, 10 and 11 clearly. 12, 12, 13 clearly. 14, 15 clearly. 16, 17, 18, 16, 17, okay, clearly. 16, or maybe we can see 18 too. 16, 17, 18, yeah, can be seen clearly now. So I'll be solving 15, by the way. So gradient descent updates, given W equals 6, that's the weight, and the learning rate 0.2, with the gradient partial L partial W to be 4. Compute the updated weight after one gradient descent step. So yeah, and then we have 17 to 17 to 19 clearly shown here. Then so in addition to 15, right, I'll be solving 20. Explain why minimizing cross entropy usually leads to better classification performance than simply counting the number of correct predictions during training. So let's go and solve these problems as we bring this whole idea home. So starting with problem 15, given W to be 6 and eta to be 0.2, partial L partial W is 4. So we want to compute the updated weight after one gradient descent step. After one gradient descent step. Okay, so let's go for that. I mean, that should be straightforward. So step one, right? Step one, we recall the gradient descent rule. Gradient descent rule, which is that the new weight is equal to the old weight minus the learning rate multiplied by the gradient, partial L, partial W. So that's the first thing. Then the second thing, as we talk about step two, so step two is you substitute the given value, substitute the given values. So we now have that W new is equal to W old. So the old W will be this 6 here. So that will be 6 minus learning rate, which is 0.2. So learning rate is 0.2, and then the gradient is 4. So, old minus learning rate times gradient 4 like this. So we know that W new now is equal to 6, 0.2 times 4 is 0.8. And then with this now, we just have the new weight to be minus, to be Your new weight is just 5.4. W new here is 5.2. No, wait. This is 0.2 times 8, right? That is 5.2, yeah? So the new weight is 5.2. So if you care for interpretation, so interpretation now, because because the because the gradient because the gradient is positive, increasing increasing the weight, increasing the weight would increasing the weight would increase the loss, right? So increasing weight increases loss. On the other side, we know that gradient descent, therefore, therefore decreases the weight from 6 to 5.2, moving it toward a lower loss solution. And that is problem 15. So let's do problem 20 now. So problem 20, we need to explain why minimizing cross entropy cross entropy usually leads to better classification classification performance than simply counting the number of correct predictions during training. Okay, so let's talk about the solution. So simply counting correct predictions, simply counting correct predictions, or what you can say call accuracy, tells us whether a prediction whether a prediction is right or wrong. You know, that just tells us, like a prediction of 90%, compare which is the highest, and a prediction of 50%, which is higher than the rest, is still correct, right? That's accurate, but then that's just accuracy. It tells us whether a prediction is right or wrong. But it ignores how confident the model is. For example, consider two correct predictions. Two correct predictions. So imagine model A. So class and probability. So for model A, it gives that the correct class is 0.51. Other class is 0.49. That's model A there. Then you now have model B. So with its class and probability, So here you see that the correct class is 0.99 and other class is 0.01. So, I mean, both models predict the correct class properly, right? However, we see that both models, both models have the same accuracy because both predictions are correct, because both predictions are correct. However, model B is much more confident and should be rewarded. So cross entropy captures this difference. So first of all, a high probability assigned a high probability assigned to the correct class produces a small loss. So a high probability produces a small loss. Two, a low probability assigned to the correct class produces a large loss. Then three, confident incorrect predictions. Confident incorrect predictions receive very large penalties, encouraging the model to correct them quickly. So as a result, minimizing cross entropy helps the model not to not only to not only to learn uh, minimizing cross entropy helps the model learn not only to make correct predictions but also to assign high confidence to the correct class. So this provides a much stronger learning signal than accuracy alone. alone, which is why cross entropy, cross entropy is the standard loss function for training modern neural networks. And on that note, we are done with this video. So I'll just show you the practice problems once more, and then that'll be all. So again, see the practice problems. Then you can clearly see questions 1 to 3 here. Questions 1 to 3, 4 to, okay, only 4 and 5 can still be seen here. 4, 5, 6, 6 and 7. Then 8 to 10. 11 to, okay, 11 to 13 should be good here. 11 to 13. 14, 15. 16 to 18. And the rest. Okay. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you have not subscribed, why not go ahead and do that right away and hit the notification bell. Subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you special privileges that you find out when you click. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Bye.